Hello and welcome. My name is Pavel. I'm a .NET component maintainer and a member of the project management committee in Apache Ignite. Today, we celebrate the release of Apache Ignite 3, and I'm going to give you a high-level overview of the product and the changes we made in the new version. This talk is for everyone. You don't have to be familiar with Ignite. Let's get started. First of all, what is Apache Ignite? In 3 words, it's a distributed SQL database. It can store data in memory and on disk, and it offers distributed computing features to process the data efficiently. Historically, most popular databases were relational and used SQL. Then, in the early 2000s, the NoSQL movement emerged, promising enhanced performance and scalability for big data. Apache Ignite rose to success by combining those 2 paradigms, delivering the best of both worlds. It scales horizontally and provides a familiar programming model with SQL. Brief history. Ignite started as an in-memory data fabric, functioning as a distributed cache between the application and the existing database, improving performance of the whole system. The second version boasted native persistence and optional SQL, eliminating the need for a backend database, making Ignite a complete solution for all your data needs. Now, with version 3.0, Ignite evolves further with a redesigned architecture that enhances performance, introduces new capabilities, and builds on its proven foundation. In other words, Ignite 2 added SQL and persistence on top of caching, and we re-engineered version 3 from the ground up with SQL and persistence in mind, improving the architecture and the integration of the components. Let's jump straight into a quick demonstration to see Apache Ignite in action. First, I'm going to bring up a cluster of a few nodes so that we have a real distributed environment here. To do that, I will use Docker. This is a small Docker Compose file which has 3 nodes in it. And the config file is very minimal. Basically, it tells the nodes how to find each other. Let's run this. And we see that the 3 nodes are now started. And let's check the log to make sure the nodes can see each other. So here in the log, we have topology snapshot, which says all 3 nodes are there. The next step is to initialize the cluster. To do that, we will use our new CLI, brand new command line control tool. You can also automate all the cluster management through the REST API, but for the demo, we're going to use the CLI, which I also run in Docker in an interactive mode. So it says you have not yet connected, and I'm going to use the default address. Now the cluster is connected to the CLI, but it's not yet initialized. And to initialize, we use this command, which gives the cluster a name and specifies a special meta storage nodes. Now the cluster is initialized and it's ready to accept client connections and execute the queries. And right here in the CLI, let's create our first table. To do that, we enter the SQL section and pass the query. So before that, we had separate tools for SQL, separate tool for management. Now it's all in one. We do it right here. Let's insert some data and see the results. The results are nicely formatted, and you can see the syntax highlighting and autocomplete is also in the tool. Now let's start with the programmatic API and use Java because it's likely the language most familiar to today's audience. And I have a minimal Gradle project here with the only dependency on Ignite client. And we connect to the cluster like this. We provide all the node addresses. The client can work with a single address as well, but it's more efficient when it has the connection to all cluster nodes. I will explain this in more detail a bit later. Let's see if the connection works. I run this program. And we can see connect to the cluster and the node name, ID, and some other information. And now let's see if we can query the data that we inserted from the CLI using the SQL API. So all the data-focused APIs in Ignite 3 are transactional now, including SQL, and you can pass null transaction object to use an implicit transaction, which will be created only for this statement. Let's run. And we can see the result of the query. It's only the value of the name column, because this is what we get from every row of the results. SQL is one way to do things. Another way is to use catalog and table APIs. We are going to do exactly the same thing, but in a more strongly typed manner. For example, to create a table, you can use an expression like this. Here we say, create a table if it not exists, with the following columns and types, with the following primary key. And underneath, it's going to generate the corresponding SQL query. So it's still the SQL, but it may be easier to work with, because this strongly typed API provides you the support of the IDE and the compiler. And this code might be easier to maintain in the future. And once we have the table, we can work with data using so-called table views. There are multiple different table views that are the way to look at the data through different types. The most basic view is the so-called record binary view. And it works with tuples. Tuple is an Ignite type, and it's like a map or a property bag, a set of column names and values. You create a tuple like this, set the values, and absort it. Again, the transaction here is null, because we can use null as an implicit transaction. Tuple is okay, but you might want to map your data to your custom class, like a person here. The person class is very basic. It doesn't have anything special about it, no annotations. And you can use it to map the data like this. Instead of a tuple, you specify the person class here, and instead of a tuple, you provide the person instance. As long as the shape of the data in the table matches the shape of your class, it has the same property or field names as the columns in the table, and types are matching, it just works. The second group of views is key value views. The basic key value view based on tuples looks like this. So instead of mapping the whole table row to a single type, to a single instance, you map it to two instances. And all the primary key columns go into the first part, and the rest of the columns go to the second part. So here we have two columns. One of them goes into the key, another into the value. And again, instead of the tuples, you can use your custom classes or simple types. For example, since we have two columns, we can use integer and string to map to those two columns. And in this case, this view looks like your normal Java map, which is kind of nice to work with when you have a dictionary table or just a two-column table. And of course, you can mix and match the APIs as you like. Now that we have inserted the data through 4 different views, we can select it through SQL. Let's run the program. And you can see all those names inserted through different views. Remember, the views are just a way to look at the data. They do not affect the underlying storage in any way. And you can mix and match the APIs as you like. That's it for Java demo. Let's do a .NET demo now. I'm a maintainer of the .NET part in Ignite. It is my baby. It's my favorite part of the code base to work on. So I'm glad to present it to you today. And we are going to do the same thing, work with some table data. Let's switch to Rider. Remember that the cluster is still running in the background in Docker. And you connect to it again, by providing the addresses of the server nodes. Let's run the program, make sure it works. And we have the connection here. We can see that both nodes are connected. In fact, we connect the first one initially and then establish the other connections in background. First, let's select some data from the existing table using the SQL API. Again, the first null here is transaction. And I run the code. We can see the result as a tuple. Again, tuple here is a property bag, but you can also map the results of the query to your custom type. So again, this record has nothing special about it, no attributes or annotations. It just happens to have the same set of columns as the table has, a set of properties. And I replace the tuple here with person. Oops. And the query still works. But instead of tuples, I get person instances. Now let's see how the table API works. First, I get the table by name. And then I have the same table views as in Java. First of them is the binary view based on tuples. And for tuples, we have this nice dictionary comprehension tables, dictionary comprehension syntax specific to C#. Then you can map the data to your custom classes. Instead of a tuple, you use person here. And then you have your key value views as well, which can be either tuple-based or specific types, be it simple types or your custom types. And to see the results of those statements, I'd like to show you my favorite part of the .NET API, which is the link provider. Link is a language integrated query. And to work with that, and a link allows you to write SQL queries using C# expressions. To start doing this, you convert your table view into a queryable by calling this queryable method. And this view is mapped to a person record here. And then you can start building your query, which can look like this. So I have filtering here, sorting, and the projection. I only need this column. And this expression doesn't yet execute anything on the cluster. It just builds the query. And to prove this, you can write it out console. Let's see how it looks. This is my query, right? This is a queryable object which contains the following SQL query here. It contains what you might expect. We select only one column. There is no overfetching. We filter it and we sort it. And we see the parameter here as well. This is the ID. And the query gets executed only when you iterate on it using a for each loop, for example. Like this. Let's run it again. And we can see the three names from the above statements. Why this is my favorite feature? Because link is just better than SQL. Instead of writing a string, language within language, here you write in the same C# language, and you get all the help from the IDE and the compiler. If I hit a dot here, it gives me the list of available columns. If I make a mistake, the code does not compile. If I refactor something, let's say I want to rename my column, here I hit rename in my IDE, give it a different name, and it's updated in the query. So you get all those maintainability benefits with link, but you keep the same efficiency that SQL gives you. That's it for .NET demo. And overall, what I wanted to show here is that Apache Ignite, from the user's perspective, can be seen as your regular SQL database. You don't need to learn any new concepts to start using it. But when you do need that extra performance and scalability, it is there for you. Just add more nodes to the cluster, The application keeps running, no code changes required. Scale up, scale down seamlessly as needed. Plus, you have compute API, data streaming, object mapping. All those nice things come out of the box. So it's a SQL database, but better. Now that we have a first impression from the demo, let's dive into the details. First, the programming API. Client connection, or thin client in terms of Ignite 2, is the primary ways to use Ignite. Your application and the database typically run on different machines. The client is lightweight, it connects quickly and consumes very little resources. So here on the diagram on the right, you can see I have two application servers. Let's say it's a web API. And those servers use an Ignite client instance to send the queries to the Ignite cluster, which is represented by two server nodes on the bottom. So the client is very lightweight, but it's also very efficient. All the APIs have asynchronous overloads, so you don't block application threads on I/O. All APIs are thread safe. A single client instance can handle any number of threads. The client uses one or more long-lived cluster connections. This eliminates the overhead of establishing connections and allows us to cache metadata locally, reducing the amount of transferred data to the very minimum. When you do the same query over and over, which is typical for most applications, we only send the data, not metadata. We already know the column names and types for that given query. Next, the connections are multiplexed, meaning that multiple active operations or queries can be handled by a single connection. And the data is interleaved efficiently over the single connection, even if you have multiple web API requests handled simultaneously. And the client knows where your data is. In a distributed database, each node holds a subset of data. The client sends key-based requests directly to the primary node for that key. We call this partition awareness. Here on the diagram on the right, we have two servers, which will typically have even split of your data. So the client knows where the specific row is and sends the request directly because it has a direct connection to every server node. And an alternative to this client API is embedded mode. Embedded API is an advanced use case. Your application and the database run in the same process, providing maximum performance by eliminating the network overhead. Compared to the previous slide, application servers and database servers are combined. The database lives inside your application. So here we had two application servers and two database servers, and here we kind of combine them together so that your application process actually contains full-blown Ignite database server node. For example, in a web shop, you might partition the data by product ID so that all the information for a given product is in a certain server node. This way, you can build the entire product page response locally. When you perform a database query, there are no network calls in embedded mode, just a function call, which is much faster. And only when the data requested by the query is on another node, we will need to make a network call. So those Ignite nodes in those in your application process, of course, are connected to each other, but they only exchange data when needed. And the local data can be retrieved instantly right here in the process. Another use case for embedded API is compute jobs, which run on the server nodes. So even here in the client scenario, when you send the compute job to the server, your code runs on the server, and it uses the Ignite API through an embedded instance that is given to your job. Previous Ignite versions were embedded first, with thin client added later. Ignite 3 supports both modes from the start. And we do it better than before because the API now is the same in embedded and client modes. We use the same types and interfaces, so you can switch between those modes at any time, mix and match, and reuse your code easily, let's say between the client and the compute job. SQL. SQL now is fully transactional. It is standards compliant. It has more efficient planner, improved index utilization. It can use multiple indexes for a single query. It supports a wider range of queries, not limited by one MapReduce step as before. And we have optimized the results retrieval. In Ignite 2, you might remember lazy mode, which affected how we pull data from different nodes for a query. Now you don't have to worry about this. There are no custom flags. You just run your query and we will pull the data in the most efficient way possible. The same goes for distributed joins, distributed DML, collocation, which come out of the box with no flags required. Schema first tables. First of all, we replaced the legacy term cache with the term table, which reflects the reality better and should be more familiar to the new users. Then, the big change is explicit schema. Ignite used to be schemaless. It would accept any data into any table or cache, then infer the schema from data for internal needs. This has all the advantages and disadvantages of a NoSQL or a document-oriented database. We found that most users appreciate the relational programming model with SQL and strict schema validation, as it guarantees data consistency and ensures correctness of your application. So in version 3, you have to define the table schema upfront, as you do with other SQL databases. Then, SQL is always enabled by default, unlike previous versions that operated as a document store and allowed SQL to be layered on top of schemaless data. Additionally, all APIs, be it key value, record-based, or SQL, share the same underlying table schema, ensuring a consistent view of the data across different access patterns. Remember on the demo we had different table views, they all operate on the same underlying structure. Transactions. Transactions use a brand new protocol based on MVCC, multi-version concurrency control, which replaces two-phase commit in previous versions. This new protocol improves performance and enables things like read-only transactions and transactional SQL. The API is more explicit now. Every transactional operation accepts a transaction parameter. We do not rely on ambient context, such as thread locals, so you can use a transaction across multiple async calls or multiple threads. Compute API has been updated to provide better development experience. Instead of a huge number of overloads for different use cases, we have job targets and job descriptors. On the server side, there is job execution context interface that provides explicit access to other Ignite APIs and current job state. And new deployment API allows you to have multiple versions of the same job or task on the server, which you can manage remotely without having to copy classes to the servers manually. So with the CLI, you have clustering unit deploy command. You give it a name, a version, and a set of jar files or class files. And then in your code, when you run a job, you specify the job class and the deployment unit, again with name and version. So you can have multiple versions of the same job available simultaneously, and you can perform gradual upgrades of your clients. Some of them may use the older version of the job, some of them switch to the new one gradually. And it's all explicitly managed through the tooling. Data Streamer has also been renovated internally and externally. We use Flow API in Java and iAsync enumerable in .NET, which are modern and standard APIs for stream processing. Those are asynchronous, non-blocking, provide back pressure control, and integrate nicely with other systems and APIs. You can either stream data directly into an Ignite table or use the receiver mode that invokes your custom logic on the server. Receiver implementation can perform additional data processing, interact with other systems, update 0 or more Ignite tables, and return results back to the client. This is like streaming MapReduce on steroids. It's a very powerful API. Ignite does all the dirty work of networking, data partition, failover, and retries. You only worry about the business logic. Configuration. Cluster and non-configuration are now fully dynamic. You can change things at runtime using the CLI tooling or the REST API. Cluster-specific and node-specific configuration are now clearly separated. Finally, we switched to JSON and HOCON formats for configuration instead of XML. For cluster management, the reworked REST API is now the one and only entry point. A single new CLI tool replaces multiple tools that we had in Ignite 2. And CLI operates through the REST API. So we have kind of dogfooding here, and both tools have the same capabilities. The CLI also has syntax highlighting with autocomplete, and it works in two modes. There is an interactive mode that we have seen on the demo. It's a read eval print loop. And there is a non-interactive mode where the tool executes a given command and exits, which can be used for scripting and automation. Internally, key architectural changes include a Raft protocol for replication instead of a custom solution in previous Ignite versions. Raft is an industry standard consensus algorithm. It's proven and trusted. It provides split brain protection thanks to the leader election and majority vote logic. And then we have pluggable storage, which means you can choose the storage engine which suits your workloads better. Out of the box, we provide the AI persist engine, which uses B+ trees, and the RocksDB engine, which uses LSM trees. LSM is log structured merge tree. In general, LSM trees perform better on write-heavy workloads, but you should always benchmark your specific use case to make the right choice. Each table can use a different engine. For SQL, we use Apache Calcite engine, which provides improved performance and standards compliance. Ignite 2 has Calcite as an optional engine, and Ignite 3 uses it by default. Finally, binary tuple is the new format for data exchange and storage. It is very compact and efficient, and all Ignite components speak binary tuple. For example, when you request a row by key from the client, the server reads the row from disk and sends it as is to the client. No conversion required. Just a quick memory copy. It's just a simple byte array. And schemas for those rows are cached on the client, so we only transfer the actual data. Column types, names, and other metadata is stored separately. And to summarize, Ignite 3 is a huge step forward for us. Every single area has been improved. We cannot wait for you to try it and provide feedback. Congratulations to the Apache Ignite community for this huge milestone. Go to the website, download it, check the docs, let us know what you think. That's it. Time for your questions. Thank you.